Hello everyone, this is Dr. Hopkins narrating the next video in our series for 472, and this is our last one on mixing of liquids. So this is kind of a summary of what we've learned previously. So we have a two-component system. If we're looking at the free energy of mixing, we have the nRT times the mole fraction part, or the ideal part, plus the nRT times the activity coefficient portion of the delta G of mixing. Okay, so we had covered that before. And now the delta S of mixing, if you recall when we looked at the temperature dependence of free energy, we know that delta S is this partial derivative with respect to T. Okay, so we would have to take the partial derivative of that. We'll do that on a later slide. Delta V of mixing is the partial derivative of that delta G of mixing with respect to pressure at constant temperature. And then we can rearrange our fundamental equations, definitions of free energy and enthalpy to solve for the delta H of mixing and the delta U of mixing. So that's just a generalized, those are the expressions we're going to use. So let's apply them to the simplest case, which is an ideal solution. Okay, so an ideal solution means that all of our activity coefficients are equal to 1, so our activities are the mole fractions, and then our vapor pressures are just related based on Raoult's law. So we're just going to have the mole fraction times the vapor pressure of the pure liquid. So then our delta G of mixing simplifies just to the ideal portion, which is due to the mole fractions. And as we've said before, since temperature is always greater than 0, this is always, and these are always less than 1, this is less than 0 for all ratios and temperatures. Delta S mixing, so if we just took the partial derivative with respect to T, we're left with minus nR of this, and so it's the negative of the partial derivative. The entropy of mixing is always greater than 0 for all mixtures, so it doesn't matter the ratio, where our entropy is always increasing when we mix these ideal solutions. And then for these three properties, delta H mix, so there's no heat of mixing, there's no internal energy change when we mix, right? These are ideal solutions, and there's no volume change when we mix. And so I did want to kind of clarify what we mean by volume change if we mix. So for example, if we mixed half a liter of one ideal component with half a liter of another ideal component, if they're an ideal solution, that half a liter plus half a liter is 1 liter. So there's no change in the total volume. It's just the sum of the volumes of our two components. Okay, so what this means is that for an ideal solution, they're miscible. All right, an ideal solution will mix at any ratio, any temperature, and it is entropically driven. Right, so there's no enthalpy, so it's entropically driven. It's random mixing, so they'll always form homogeneous solutions, and we get no heat of mixing because basically what we're saying is all of the pairwise interactions, all of the A to A to B, and B to B are all identical in terms of intermolecular interactions. So that defines an ideal solution. So let's do a non-ideal solution in terms of mixing. Okay, in this case, our activity coefficients, 1 or both, can be different than 1, right? So they're not equal to 1. So our activity is no longer just our mole fraction, but it's activity coefficient times the mole fraction. And then we adjust our Raoult's law to add the non-ideality part. So we have the activity coefficient times the mole fraction times the vapor pressure of the pure liquid. And that gives us our vapor pressure. Okay, so let's do delta G of mixing. Let's look at the free energy. And so I've just simplified it to the delta G mixing ideal. Here we have our activity coefficient term, which we're going to redefine as, or we're going to define as the excess, this GE excess Gibbs free energy function. Okay, so then I've just taken that second term, and you'll notice this is less than 0 if our activity coefficients, and that's kind of the sum of the activity coefficients, is less than 1. It's greater than 0 if they're greater than 1. So if we have large activity or a larger than 1 activity coefficient, we're promoting immiscibility. If we have less than 1 activity coefficient, we're promoting miscibility. We can do the same thing for delta S mix. So delta S mix is delta S mix ideal plus the excess function. Well, now the excess function, let's just do the partial derivative of the Gibbs free energy excess function with respect to temperature. So if we do that, we have the partial derivative of T. We pull this part out, but we can't assume that the activity coefficient is independent of temperature. In fact, what we're describing our activity coefficient as the intermolecular interactions between the two molecules involved. Clearly, that's going to be temperature dependent. So there could be a temperature dependence, so we need to evaluate that in terms of the partial derivatives. So that would be our excess entropy function. It's not an easy thing to evaluate because we would have to know exactly how that changes with temperature, and we haven't got a function for that yet. And then the heat of mixing, of course, ideal, the zero. So all of the heat involved in mixing is an excess heat or excess enthalpy. And we can do it, we can rearrange and set up our expression this way, and we're left with this term, so minus nRT squared, once again, because we don't know whether the activity coefficients are independent of temperature. So if they're independent of temperature, these terms will go away, and this would also be zero as well. All right, and then the last one is delta V mix. I'm not going to show delta U mix. You can rearrange that as well. Is the excess volume, because the delta V mix is equal to 0 for ideal. It's this partial derivative. And once again, we don't know whether the activity coefficients are independent of pressure in both cases. And so that would be our mixing for non-ideal solutions. If you want to think about the big difference, the one component, we're adding just this coefficient. It contains all of our differences between ideal and non-ideal. And so if we want to just kind of simplify it in terms of pairwise interaction energy, so we think about our activity coefficients. If we have one that's greater than 1, so gamma A and gamma B, what we're saying is that the pairwise interaction of A likes A better than A likes B, or B likes B better than B likes A. And that's what it means to have an activity coefficient greater than 1. It likes to be with something like itself rather than the other one. If the activity coefficient is less than 1, that means that A likes B better than A likes A, or likewise B likes A better than B likes B. So we would have activity coefficients less than 1. Or you could have a case where your average interaction energy, AABB, is less than the interaction energy between A and B. In that case, the sum or both of those activity coefficients is going to be less than 1 because this interaction is greater than those. If this interaction is less than the average of the pure liquid interactions with each other, then our activity coefficient is greater than 1. So in a case where we have overall activity coefficients greater than 1, that means in terms of volatile liquids or volatile mixture, your escape tendency increases. So we're going to be overrepresented in the vapor where they're going to not interact as much. And if it's less than 1, the escape tendency is going to decrease compared to ideal, and you'll have more in solution than you would expect if you were an ideal solution. And so that's the kind of physical interpretation of that one parameter we've been using to redefine whether you're an ideal solution or a non-ideal solution. And until next time.